1080 hot rolled steel. So hot rolled steel bar has been machined to a diameter of 1 inch. It is to be placed in reversed axial loading of 70,000 cycles to failure in an operating environment of 650 Fahrenheit. Estimate the endurance limit. So that's one question. And the fatigue strength at 70,000 cycles, assuming the reliability for the endurance limits estimate to be 99%. So there's a reliability limit, and ultimate tensile strength SUT at 70F to be 112 kPsi. So we can write down everything we know. We know that it is the diameter is 1 inch. We know that the cycles are 70,000. We know that the room temperature is 70 Fahrenheit. We know that the operating temperature is 650 Fahrenheit. We also know the reliability is 0.99%. And we also know the ultimate strength at room temperature at 70 is 112 kPsi. Okay, so what is asked of us is to compute the endurance limit. SE is unknown, and the second, let's call that 1, and the second part is fatigue strength. That should be SF. Okay, let's think a little bit about how we might compute SE. One way of computing SE is if you know Ka, Kb, Kc, Kd, Ke, then we can use this formula. And for SF, it's normally, if you know A, N is to B, N is 70,000, A and B are, let's write what A and B is. A is a formula which we have derived earlier. A was F times SUT square divided by SE, and then B was 1/3 log SE divided by FSUT. Okay, so seems like you would need SE to do this second calculation. So unless you have SE in the first calculation, you can't do the second part. SUT is probably known. F, we know that's from a table. So it's clear that we need to do part 1 to solve for part 2. So let's solve for part 1 first. Okay, now the question is how many of these factors we need to take into account. Let's go through them one by one. Okay, so if you go back to this whole table, Ka is a surface factor. You need to watch out for words like the surface finish. Okay, we need to see if any of the words are there. So if you see here, it's actually told that it is hot rolled. So hot rolled is the keyword. So is there a factor for hot rolled? We go here, we see that hot rolled has a factor A and a B. We are dealing with kPsi. So we go back here, look at the factor for kPsi. It seems like it is hot rolled kPsi. The factor A is here. We don't look at the MPa factor and look at B, which is here, minus 0.65. So 11 and minus 0.65. And the formula is here. So that's Ka. Let's compute Ka. Is A times SUT raised to B. A is 11. SUT is 112 12 kPsi. That's right. Well, that SUT is at room temperature, 70 degrees. But what we really need is, since this part is operated at a different temperature, elevated temperature, 650, then your ultimate strength is not going to be 112 kpsi. It'll actually decrease. So if you put 112, that's not the right way. So clearly, we need to first um, figure out SUT at the operating temperature. This is not known, 750. Okay, so we cannot proceed, sorry, 650. We cannot proceed with Ka because we do not know what this is. So let's first try to go through the temperature effects. Without the temperature effects, we can't really proceed. So we can't do this unless we know the ultimate strength at uh, 650. That's what we'll have to do. Okay, so let's look at the factor KD before we get along with this. So what this is going to help us do is it's going to let us compute what SE prime is, because SE prime is unknown. So we can use the we need uh, SUT at temperature, which means that we need to first get it from this. So basically we start from here. This is basically telling you how temperature affects the ultimate strength. So let's go with this. We are given temperatures in Fahrenheit. So I'll take this formula. Okay, so let's see what we get for this. ST divided by SRT is 0.98 plus 3.5, 10 raised to negative 4. TF is 650 minus 6.3, 10 raised to negative 7, 650 square. So S T, which is 650, divided by S, room temperature, which is 70, is equal to 0.94. Yes, so this is step 1, step 2, sorry, step A. Step B, this is from KD. Step B here, well, this was step 1A. Step B is we need to compute the ultimate strength at room temperature using this formula. So I'll write it down. S T, sorry, SUT at operating temperature is the ratio of ST divided by SRT times SUT at room temperature. So SUT at 650 is 0.94 times SUT at room temperature. I think we know this. So if you go back and you look at this question, you know SUT-RT at 70, it's 112 kpsi. This comes out to be 105 kpsi. Okay, so we got SUT. Okay, so what's the next step? So here, once we get this, then we can estimate SE prime using these formulas. Now, here we need to look at what SUT is at the operating temperature. Let me just copy this and then we can stare at it and figure out what's the right one. So we're using the kpsi units. P spot C. You can copy it from KD. Okay, so SE prime is going to be, well, it depends on what SUT at 650 is. It's basically 105 kpsi, which is less than 200 kpsi. So we need to use 0.5 times SUT at 650. So 0.5 times 105. And so SE prime is 52.5 kpsi. And then one benefit of doing all this is that we already have now computed KD and SE. So the step D is KD is 1. KD is 1. I wouldn't put SE equals SE prime because SE will depend on other factors. Maybe we can put it there if you want. KD is 1, and this is the one which we'll use, 52.5. Okay, so we sort of digressed, but it's all because we don't know what SUT was at temperatures other than room temperature. So we can actually go back now. So something which we had left this. So we can take this again and compute it. Copy. So SUT at 650, I believe we've computed it somewhere here. SUT at 650, yeah, here it is. SUT at 650 is 105 kpsi. We have it. So let's call that 1 just to refer it, or use a different symbol. So 11. Though if I remember, it was that's right. So when you do the math, it comes out to be 0.534. Okay, that's AKA KB. It is for rotating ground specimen. You could also have a non-rotating ground specimen. It's just a matter of figuring out which of those it is. Has been machined to reversed axial loading. I'm going to assume that it is rotating in the absence of anything else. So let's assume it is rotating. Maybe the reversed. No, that doesn't tell. It's axial loading. Yeah, I'm going to assume it's rotating and see what the factor is. So KB is 1. Yeah, so I think it's immaterial if it's rotating or not because this is axial loading, KB is 1 no matter what. So even if it's, let's say if it was non-rotating, all that non-rotating does is it gives you an equivalent diameter, whatever that is here, but the equivalent diameter doesn't do nothing for axial loading because KB is equal to 1 no matter what. So we don't really care if it's rotating or non-rotating because it's axial loading. So we are all good there. So we don't need to assume anything. This don't need anything. So KB is 1. Let's go to KC. Okay, so KC. KC is here. So this is a loading factor for axial loading. It is 0.85. That's what we'll use. Axial. Next is KD. So KD, we went through this whole recipe where SC prime is unknown, and we figured out that KD is 1. So that's what we'll use. So if you go to here, this is where I figured out that KD was 1. That's what I'll use. KD equals 1. And then finally, there's a reliability factor, KE. You could either use this formula and use ZA from here, or they actually have given it to you at 99% reliability, which is this. We have 0.814. KE is 0.814. This is at 99% reliability. Okay, so we all set to compute the endurance limit. SE, it's KA times KB times KC times KD times KE, SE prime. KA is point, this is KA, 0.534. KB is 1, KC is 0.85, KD is 1, KE is 0.814, and SE prime, this is something which we will use the calculation we did for SE at the temperature of 650, it's 52.5. So this is at temperature of 650 Fahrenheit. Yes, I'm going to crunch these numbers. So I get 19.39. So that's my first answer. Okay, so that's part one. If you look at part two, we are equal to compute SF. For that, I need to compute A and B, and then N is 70,000. So let's compute A, B, and go from there. So for part two, A is F times SUT, the whole thing squared, divided by SE. Okay, and then B is 1/3 log SE divided by FSUT. Okay, so we still need to compute F. Let's see how to compute F. For F, well, let's go to F. It should be here. Okay, F is a table. Well, it's the two ways to do it. One is to use the graph here, or to use this formula. It's really up to you. It just seems simple to use the graph. So what we need here is, this is a plot of SUT versus F. So unless you know SUT, we cannot compute F. So we need to get SUT. So for that, we go back to the problem and try to figure out what SUT is. I think I did it here. Okay, so SUT, there are two values. One is the value at room temperature. So this is the value at room temperature. It is 112. And then there's a value at the operating temperature, which is this one. It is 105. Okay, so the one you'll use will be at the operating temperature. So operating temperature is 650. So we have 105 kpsi. So SUT at T, SUT at T, or SUT at 650 is 105 kpsi. So we go back to this chart, see 105 kpsi. It looks like it's here. Okay, so it looks like it's I don't know, it looks like it's more than, it's very close to 0.84. but it can't be 8.83 because 83 should be somewhere here. So I don't know, let's just stick with 0.84 because it's just easier to use it. Otherwise, trying to figure out the value could be. So just use 0.84. So here we, oh, sorry, wrong place. Okay, so we have at S ut equals 105 kpsi, F is 0.84. So C lecture 17 notes. Okay, so do that. And so we have F, we have SUT, and we also have SE, which already computed in the previous question. So we can compute A. So A is F.84 SUT, which is 105, the whole thing squared, divided by SE. SE is 19.39. Let me compute that point. Divided by 18.39. So it's 401.2. So B is 1/3. This log is natural log. SE is 19.39. F is 0.84. SUT is 105. The log of 19.39 divided by 0.84 times 105 minus 0.65. Oh, divided by 3. I forgot that. Minus 0.22. So we have B, we have A. The last thing we need to do is SF is A n raised to B. A is 401.2 and is, I think, 70,000 cycles. 70,000 cycles. B is minus 0.22. So SF would be and 1 times 70,000. 34.47. The units would be kpsi. Okay, so that took some time, but that's the answers we worked out. So this, I think, question sort of shows you how to go through the entire process of computing SE from the various factors and then puts it together in that SN curve equation to compute the fatigue life.